So, while we are dealing with the technical issues, which are dealt with already, so we have today here Taylor Baird, also from EPFL, and he's going to talk about OSSCAR. Is OS like the double S because of Python snakes, or oh, that's like okay. Okay, you'll tell us in a sec. Okay, cool. Good luck.
So yeah, Taylor, I'm a PhD student from EPFL doing computational physics. And I'm also part of the development team of OSSCAR, and I'll talk to you all about this today. So OSSCAR, as you can see, stands for Open Software Services for Classroom and Research. And it's an initiative that started at EPFL in 2019, whose objective is to create a collaborative environment for instructors in computational sciences where they can go and find and share interactive visualizations which are tailored towards education and teaching and which adopt an open science approach. And the fundamental philosophy underlying OSSCAR is depicted in this figure that you see here. In the project, we aim to foster a feedback loop between teachers, students, and researchers, where each of these parties can go to the project, find material that is useful for their own respective purposes, and if they choose to do so, contribute back to the project, thus closing this loop. To give you an idea, instructors can find in the project pre-existing lessons that have been developed by other instructors, which they can then use for their own classes. If the exact lessons that they're looking for aren't present already, we provide tools which streamline the creation of new lessons that those instructors can then choose to, if they want, contribute back into the project for use by others. On the part of students, they have access to high-quality, hands-on lessons which provide an enriched learning experience, which helps them learn faster and gain a deeper knowledge of a subject. Moreover, all the lessons are created in a way which really promotes open science, and so those students are encouraged, if they're interested, to go into the source code behind the lessons, modify it, improve it, and perhaps contribute back with new lessons to the project. Moreover, as we'll see later, OSSCAR really promotes a reciprocation between research and education, and many of the tools that have been developed within OSSCAR for a teaching context also find use in research contexts, and vice versa. So OSSCAR primarily targets two different use cases in education. The first of these is as live demos in classrooms. This is when a teacher would use one of our lessons, which are essentially Jupyter notebooks that have been converted into web applications and then hosted on the cloud. And they would use these to go into more detail for a method or a concept that they've already presented to the class in a more traditional fashion. The second use case is as takeaway home self-learning exercise booklets that students can use under their own steam without instructor supervision. And you can see a couple of examples of these lessons to the right of the screen. All the lessons thus far come from two courses that are taught at EPFL, which target quantum mechanics and atomistic simulation. The first of these examples that you can see is showing students the phenomenon of the avoided crossing in quantum mechanics. And the second example shows the method of constructing norm-conserving pseudopotentials, which is a method routinely employed in material science. Now, I'll give you a demo of that first use case, so a live demo, but you should bear in mind that all of our lessons are created so as to accommodate both types of those use cases. Now, the crucial ingredient for both use cases is this ability, the provision to students of the possibility of really looking at the underlying relationship between the phenomena that is presented in the lesson and the underlying physical parameters that govern that phenomena. You can see this going on in these examples. Students are essentially able to play with some widgets which modify the values of those parameters and immediately see visual results of the effect this has on phenomena. We can also envision one third use case for OSSCAR lessons, and this is in graded notebooks. And we're also pursuing this avenue as part of a collaborative project with the Cosmo Lab at EPFL, where we endeavour to facilitate easy creation of graded notebooks that can be created by instructors and given to students, which typically include a small coding component. A little more on this later. So I'll quickly go through each of these points here, which are the approaches taken within OSSCAR and the contributions generated by the project. I'll go through each point in more detail in subsequent slides, but just to list them bullet points here. And the project really aimed to use well-established software. OSSCAR is an inherently open science project, and so we use open source software whenever possible, like Jupyter, Voila, IPy widgets, etc. But when the existing standard technology doesn't fulfill all the necessary requirements for our lessons, we go in and contribute with our own components to meet those needs. We develop educational content. You saw some examples from courses at EPFL. So far, the courses target computational chemistry, material science, and physics. And we also aim to facilitate creation of new content, new lessons by instructors inside EPFL and out with. And we do this by providing in-depth documentation on how to use each of the ingredients that go into the creation of one of our lessons, with examples of usage of each of these, and also, as I said, by providing new widgets that can be incorporated into those lessons. And throughout all of this, we encourage computational thinking on the part of students and really promote the contribution of those students back into the project. So, in terms of the use of well-established software, in OSSCAR, all of our content is developed using Jupyter, Jupyter Lab, with Python as the underlying programming language. And we opted to use this because Python is ubiquitous in our field, and it's very easy to develop complex applications with very little code. Moreover, there's a lot of good libraries available for a variety of applications, like 2- and 3-dimensional plotting, data analysis, machine learning, etc. Moreover, the Jupyter ecosystem really makes it easy to add graphical components to our lessons, all in Python, no need for an instructor to have in-depth knowledge of background JavaScript. And moreover, Jupyter also provides tools to convert these notebooks into web applications, which, as we'll see, is a crucial step in creating one of our lessons. So, as I mentioned, there are situations where the standard widgets available in libraries like IPy widgets don't fulfill all the requirements of our lessons, don't allow us to provide the students with the entire range of flexibility that would allow them to take the most away from a lesson. And so when this is the case, we've developed some customized widgets, which you can see 2 examples of here. In this topmost example, there is a widget which allows the visualization and analysis of electronic band structure and density of states of a crystalline solid. This is something that's routinely done in computational material science. And moreover, and since this is such a common workflow, having a widget that allows researchers to do this visualization in a Jupyter notebook really streamlines their workflow, expedites their research. Moreover, since it's a core concept in material science, being able to have students, rather than just see these plots in a textbook or on slides, they can go in and actually play with them and see how small changes that they make to parameters affect the plots, really allows them to ingrain the concept in their mind. We have another example of a widget, the second one down here. It's a custom widget that allows visualization of the first Brillouin zone of our crystal structure, another routine piece of work done by material scientists. And both of these widgets have been incorporated into research tools that you can see demonstrated in previous talks at SciPy. They've been incorporated into AIDA, which is a Python interface for automating workflow in material science. And So we can see here how OSSCAR has taken these widgets from an initially research-oriented context and transferred them through the project into teaching context where they can be used in educational notebooks. In terms of encouraging and facilitating creation of custom content, we have an in-depth set of documentation which is available at the main point of entry to the OSSCAR project at www.osscar.org. I'd invite you to check out if you're interested. All of our material is also available open source at our GitHub project, which is linked here. An upshot of this is making it simple for instructors to reuse educational content, so avoid duplication of effort. They can reuse content created by other instructors. And moreover, this library of code examples serve as a template to create new content. You can see how it was done in one case and adapt it for your needs. We also took special care at the beginning, the outset of the project, to investigate different approaches for deployment of these lessons. And by deployment, I mean taking them from notebooks, converting them into web apps, and then hosting them on the cloud. And this is important because for a few reasons. Firstly, we really want students to have zero work, essentially, in setting up these lessons. Rather than having to go through steps of installation locally, students should be able to just paste a link into their browser, click enter, and have the lesson available to them. Moreover, ideally, we want this deployment to have minimal waiting times. So in that first use case I mentioned earlier, if an instructor is going through a lesson in class, they don't want to have to wait for the lesson to load and students to lose interest and focus when they're trying to go through a topic. And so later I'll go through different options for this deployment and discuss pros and cons of each. As it stands, we have a curated library of lessons that you can find at our website. These cover a range of subjects in statistical mechanics, quantum mechanics, material science, and molecular dynamics. This slideshow shows some examples of these that you can check out at the course application section of the website. Now I'm going to go through one particular prototypical example of an OSSCAR lesson. It's going to look at the Verlet algorithm, which is used to solve the equations of motion that govern the behavior of a body governed by Newton's laws. But the exact details of this aren't important. I'm really just using it as a concrete example of how the structure of a OSSCAR lesson looks and how it flows. So I've just clicked a link using one of the deployment options that I mentioned earlier. This opens the notebook, which is hosted on a Doku server at materialscloud.io, this URL. All of our lessons have the same uniform, standardized look and feel, and this was a decision made to really make it so that students have a common user experience when they're going through the lessons. We use a customized Voila template to have this custom style and our OSSCAR logo displayed at the top of all lessons. Each notebook starts off with the title and then a list of authors. So here we see my colleague, Dodu, was the sole author of this notebook. We choose to include a list of authors to really acknowledge work done and contributing to the project and encourage further contributions. Next, we have a link to the source code for the notebook itself, which a comfortable student can go into and modify, play with, and have a look at exactly what's going on under the hood if they're interested. And then following this, we have a set of goals or learning objectives for the notebook, where this really serves to direct the student's usage of the lesson. We have a couple of goals that more pertain to background theory of this lesson, and then one which will only be attainable if the student really gets hands-on and explores the concept through interacting with the notebook. We store all the background theory for this lesson in a separate notebook to keep the main interactive notebook uncluttered. And I'll just click on this to give you an example here. We really try and keep this minimal and link to external sources whenever possible to give students like some background reference material, but only a minimal amount to let them use the notebook, as they should already see this concept prior to going through the notebook itself. Following on from this, we have a set of tasks and exercises, again, guiding the students in their usage of the notebook. These typically take the form of asking them to play with the parameters on the control, the visualization in the notebook, and then make observations, and based on their knowledge of the background theory for the lesson, answer these exercises. We provide solutions, but these are initially hidden to try and encourage students to answer themselves first. But having solutions present means that we also accommodate that second use case. If students are going through this on their own without a teacher, it's nice for them to have access to solutions when an instructor is not able to give the answer. Okay, so the next part of the notebook is the main visualization section. Here we have a two-dimensional plot of a Sun-Earth system. Now the Sun's going to orbit around the Earth in an elliptical orbit. The Sun's shown as a red dot. The Earth is a big yellow blob, and its orbit's traced out as this black line. We're asked in the very first question to choose a small time step and observe how the Earth orbits around the Sun, and check how total energy and angular momentum evolves in time. I should have mentioned, we also have plots here to the right of the main visualization showing the evolution of the energy of the Earth and its angular momentum in time. And we have the time step for this Bernoulli integration scheme is already preset to delta t equals 1. So if we look at this, we see that indeed the Earth's orbiting around in a stable elliptic orbit. Our energy and our angular momentum are conserved. They stay at the same value as time proceeds. And this means that our algorithm's doing the right thing and properly solving those equations of motion, as we know that energy should be conserved and angular momentum should be conserved if there's no external forces present. The next question asks us, does the Earth still remain in the same orbit when a large time step's used? And try to explain the observations. So let's try a larger time step, press play, and observe the behavior. What we now see is that we no longer have this stable elliptic orbit. Subsequent orbits are not superimposed. And we also see that we have a breakdown in conservation of energy and angular momentum. Now, students having learned about the background theory of the Bernoulli algorithm will be able to relate this to the fact that using too large a time step renders the algorithm unstable. And this really ingrains in the student's mind this relationship between stability of the algorithm and the choice of the parameter controlling the algorithm. And it's an invaluable test when doing these kind of simulations to look at how energy and angular momentum evolve in time to see if you've chosen a sufficiently small time step. Students will really take away this message by seeing this play out in front of them. Finally, the last part of the notebook is a legend and a set of instructions on how to control the visualization and use the widgets. Again, this is important for that second use case. If an instructor's not present, then it's helpful to have some instructions for the students so they can know how to use the notebook without input from the teacher. Okay, so just going back to the main presentation, I'll now quickly give you an overview of the different technology that went into creating a lesson like this. So just as an outline, the fundamental building blocks of an OSSCAR lesson are Jupyter widgets whenever possible, and the vast majority of the widgets we use come from IPy widgets. We use plotting libraries like matplotlib or plotly. Again, we create custom widgets when necessary. We then need a method to take the notebooks and convert them into web apps. And for this, we use Voila. I'll mention a couple of alternatives later and why we chose Voila. And finally, I'll go through the different options for deployment. So yeah, we use standard widgets from IPyWidgets when we can, and this really gives us the core component for these lessons. This the callback functions between widgets and visualizations is what allow us to give this kind of visceral experience to students, allow them to see the effect they have on phenomena when they change parameters that control the phenomena, like or method, like you saw with the change in time step before. Now, there are situations where those standard widgets from IPyWidgets don't give us all the range of functionality that we need. And when that's the case, we go ahead and develop our own custom widgets. This involves essentially using some templating software and then actually writing some more complex JavaScript for the front end and Python for the back end. And since this is a bit of a time investment, we try to target custom widgets that are as versatile as possible, cover as many use cases in the community as possible. And one example, you saw a few before, but another is this widget here, which is a periodic table widget. And this allows students to really visualize chemical trends in a host of classes on chemistry, material science, physics. And moreover, this widget is also found use in research, where it's used to filter through material databases in this Optimade client, open databases integration for materials design. You can choose which elements to include in a search, which to exclude. And lastly, as another example of a custom widget that targets that third use case of graded exercise booklets that we created, was a code input widget. This is a widget that you can see playing out here. It essentially renders a code editor in the output cell of a Jupyter notebook, which a student can go in, type the function body of a Python function, and have this be run interactively. This has been incorporated into the SciCode widgets project that we're undergoing as part of collaboration, also with the Cosmo group at EPFL, and these lessons that have been developed within SciCode widgets are used in a course called Introduction to Atomic Scale Modeling, which is taught by Michele Ceriotti at EPFL. Essentially, the lessons would consist of a mixture of widgets, similar to what you saw in the demonstration before, that really display or demonstrate a concept, and then have this code input widget that allows students to type up a little bit of code to answer questions related to that concept. And if you're interested in this, you should check out the poster later today by my colleague Alexander Kozinski on SciCode widgets. Okay, so next we need a method for converting our notebooks into web apps. For this we use Voila. We chose Voila because it allows this customization that you saw in the lessons before, and the possibility of creating standalone web applications. There are a number of other options like MB Convert, App Mode, etc. But Voila, we find, really satisfies all the criteria we're looking for. Finally, there's a number of options for deploying these web apps to the cloud. You have My Binder, which is nice as it's a free option, and it doesn't really require much knowledge of like setting up a server, like Docker or whatnot. However, it can suffer if you're trying to do something computationally demanding, and it takes quite a while for these web apps to load using Binder. Docker, on the other hand, offers a much faster alternative. However, it's not free, and for us, we were using a private Docker server hosted at materialscloud.io. But if you want really computationally intensive applications, this is a good option. Lastly, there's the option of Jupyter Hub. We also host our lessons at the institutional Jupyter Hub at EPFL called Noto that you heard about earlier. And this has a number of advantages, like integration with Git. So, yeah, just in summary of that, OSSCAR gives a complete streamlined solution to develop and deliver these web apps for education. And I'll just conclude by saying that at the moment, we believe we've created the foundation for that collaborative environment we set out to create at the beginning. And we now really ask you, the community, if you're interested to check out the project and get in touch if you think you'd be interested in contributing with lessons or materials. And if you are interested, I would recommend you go to our homepage where you can find a guide on contributing and how you go about contributing new lessons. And reach out to the project managers of OSSCAR. So this is Giovanni Pizzi and Sara Bonella, the contact details of whom you can find at the team section of our website. And finally, I'd just like to say thank you to everyone that made the project possible. So to the Open Science Fund at EPFL, CCAM and Marvel for dissemination and development. Thank you to Noto for all the help in actually hosting the lessons and also just advice given. Students for feedback on the notebooks. And then I want to say a thank you to all my colleagues who've helped me since I joined the project. And yeah, just last note is do go and check out the project if you're interested, and the links are here to our GitHub and webpage. And thank you all.